to do tomorrow to get all the videos off the cloud. We'll post them up for you guys. Okay. Just as a reminder, we've been talking about resistance training. You guys remember that, right? Yes. Okay. Very bro-ish, very resistance training. We've been working our way through talking a little bit about some of the models of things and how this is going to go, right? Single cells, animal models, some human stuff. We were talking about the idea of repetitions, of load, of the number of days per week, and what we know about those things contributing to hypertrophy, okay? So as I told you guys, there's not a lot of data. There's really not a lot. There's more than just this. This is kind of an overview, but there's not a lot. Most people, when they do training studies, do 2 or 3 days a week for the most part because we know that works, okay? Now, there is some evidence, and I haven't shown it to you guys here. I apologize, but in untrained people, okay? Untrained people, 1 day a week, okay? For maybe the first 6 to 8 weeks or thereabouts, 1 day a week at least gets us strength increases that are reasonably similar to 2 or 3 days per week or 4 days per week, okay? There's even some evidence of 1 day a week, 1 set of 10 repetitions. If it's to failure, I can do 10 reps, I can't do 11, may work. Once you cease to be untrained, which is in about, a month of all of that, then the effect begins to lessen, okay? It begins to lessen. And we probably need to add another set or 2 and another day of the week. But basically, if you're untrained, doing anything is going to work, okay? Anything is going to work, especially strength-wise, okay? So I say all of that to then say, let's look at this particular study, okay? This is from a group, and to me, this is one of the 2 or 3 best sort of resistance training, underlying physiology, kind of what is the stuff that drives hypertrophy group in the entire world. This is from a group at the University of Alabama at Birmingham. The guy that runs the lab is named Marcus Baumann, and they're tremendous, okay? They're tremendous. What you can see here is this is myofiber cross-sectional areas. This is cross-sectional area from biopsies, okay? From biopsies. These are in somewhat, not older adults, but people that are sort of my age and kind of a little bit older. So not college age. And what you can see from all of this, okay, what we can see is they've got men and women in the kind of gray and in the white, all right? And what they did is the first 2 bars here that I put up in green, this is their initial 4 months of training. So this is 16 weeks of training, okay? So what they've got is they did 3 days per week, okay? 3 days per week. And these are in 2 sort of separate groups of people. But what you will note is this kind of general increase in size that's going to range. We've gone up about 1,000 micrometers squared, maybe a little bit more than that. So about a 25 to 30% increase in size in the first 16 weeks. Okay, pretty standard, right? Pretty standard. That 15 to 20% increase is about what we would normally expect. Okay. Then, and I think this is really important. Okay, you guys will learn, if you haven't already in life, life gets busy. You have a toddler and she's crazy and she runs around and she wants your attention all the time, and you have 7 graduate students who need your attention and undergraduates and classes to teach, and just life is busy. Okay. What they did was train people up. Now let's see if we cut back on stuff once we've done this, how much of our gains in muscle size, what's like the minimum amount that we can do to hang on to whatever it is that we had already accrued. Okay? So Brady's going to train hard for 16 weeks. Matt's going to train hard for 16 weeks. Brady's then going to dial it back to do a 1/9 volume maintenance. So this is, imagine 3 days per week, 3 sets of an exercise. He's then going to dial it back to 1 day a week at 1 set of that exercise. Matt did 3 days per week, 3 sets. He's then going to go to 1 day a week of 3 sets. Okay, so a 1/3 or a 1/9 of our volume that we're going to see. Okay, and so we'll start on the bottom. I don't know why they flipped the graph this way, but in our group that we did, sort of we went from 3 days a week to 1 day a week. Their guys continue to get a little bit bigger. Okay, a little bit of overload. They went another 16 weeks, and then another, because they basically went out for almost an entire year. If we look at all of this, okay, and so they continue to get a little bit bigger. And then if you look at the mean, where they're kind of graphing the means in this line, they're about the same, and they hang on to pretty much everything. But our 1/9 volume, this is 1 day a week, 1 set after we've trained you. It dips a little bit, although it's not statistically significant. It's still elevated from pre, and they mostly hang on to whatever they've got. Okay? And so they're not getting bigger beyond that initial phase. Is that because they reached their genetic potential in 16 weeks? Probably unlikely. Okay? Probably unlikely. But they could at least hang on to what they could get. Okay? And so I think this is really important. It tells us some stuff about plasticity and things in the nervous system for those of you that want to go on and work with actual clinical patients and those kinds of things. Then there's this thing, if we can train people to a place, you can really begin to cut back on what they're doing. You don't have to invest as much time, and they can maintain their gains. Okay, and this is potentially good from an exercise adherence standpoint. Can you get 1 day a week where you can get 1 set of exercises in, right? Can you find 1 day? It's harder than you think. Okay, you know, I was a master's student like you guys. I taught 3 weight training classes. Guess what I did during my weight training classes? I just did weight training, right? We got to go work out and do those things. We didn't check anybody in. We checked in, then we lifted and all of that. It was great. That semester I taught golf. I had 3 golf classes. My golf game was in good shape. I just played golf. So same kind of an idea though. Let's do as much to kind of hang on to it. All right. So I think that's another thing to kind of keep in mind as we look at this from a global perspective. Okay. Okay. Coronavirus. All right. I'm going to show you guys these data because they're weird as hell. Okay. I was given these data on my doctoral comprehensive exams and asked to explain them. And there is no explanation. It was a question like I asked you guys. Like, here's some things, offer me something. There's not really a right answer, or there might be some wrongs, but there's not really a right answer. This is an animal model of work. This came from the guys from Greg Adams, who worked in a group at the University of California at Irvine. And this is medial gastroc muscle mass, right? So this is milligrams per body weight. What they did was they basically cut the medial gastroc out of these mice. And so they had these mice, and they sort of would anesthetize them, and then they would do like E-stim. They'd stem their, I think it's the perineal nerve that goes to the medial gastroc. They'd stem the nerve and then make them do either isometric exercise, shortening or concentric exercise, or lengthening or eccentric exercise. And they basically normalized all of that so that the time that the muscle was being turned on by the stem, right? They sort of did a force and a time thing and multiplied all of that together so that all of these things worked. Okay? And what you can see then is that all 3 types of contractions seem to cause an equal amount of hypertrophy. which would tell us that if we had Chris stand up and she just pushes on the wall as hard as she can every day, that her quads would get just as big as if Richard was doing knee extension exercise, or if Cy was doing eccentric knee extension, so weight is up and then lowering it down. As far as I am aware, there is not data in intact humans, okay, that shows this exact thing, okay? Anybody interested in this? Make a nice, it's probably more of a dissertation project than a master's thesis, okay, because you got to train a bunch. Nobody knows. This baffled my PhD advisor. He was like, this should not happen, okay? But it does. The isometric exercise should not cause hypertrophy, okay? We have some evidence in people that isometric does not seem to cause hypertrophy, okay? Is it the animal model? Is it the way they were doing it? Is it how long they were stimming them? Not 100% certain, okay? But there is some evidence that maybe they all work, all right? Again, things that don't always translate from animals into people. So what do we see now? What are some data in people? Okay, so here are two studies by the same group. These are folks that are coming out of the University of Texas at Galveston. And I've forgotten, oh God, the guy's name that's in charge there. But this is some protein synthesis rates on things. I'm sorry, the guys, it's Bob Wolf's lab and all of those guys that are down there. So here's myofibrillar protein synthesis rates, okay? And then this is the sort of net area under the curve of the protein synthesis rates over the course of like 9 hours after a single bout. This is one bout of exercise, okay? And then here is some pre-post stuff as well. This is actually in people, okay? What you can see is here's their resting protein synthesis rates. Here we have black are eccentric, hatched is concentric. They're calling them lengthening and shortening. Okay, we see with this, and then this basically is the average. It's the area under the curve of all of these. What we see is that eccentric contractions seem to drive a little bit bigger of an increase in fractional protein synthesis rates. Okay, a little bit bigger. There's something magic about lengthening the muscle. Okay? I'll show you guys some addition there, but there's something magic about lengthening. Okay, we get a little bit more. Is it because we can generate more force eccentrically? We get more force on fewer fibers, so it stimulates those. Does it cause a mild amount of muscle damage, which helps to activate the satellite cells? We don't really know. Okay, so there's a little bit of stuff here. Here's a later study where they're doing lengthening. This is muscle. This is actual cross-sectional area. Okay, from a training study. I believe this one was like 12 weeks. Eccentric only, concentric only. Okay, and they're basically the same. Although if you squint really, really hard, maybe you can see it's not statistically different, but maybe there's a little bit more that's going to be there in the eccentric side. Okay. So again, our fractional synthesis rates don't always translate into sort of whole body measurements or even biopsy measurements of things. Okay? So there's not a lot of human data comparing on to ACT and the like. Okay. Here are some other data. This is from John Farland Jr., who is at University of Saskatchewan now, I believe. So it won't mean anything to you, but one of the girls who was in the lab with me went to work for his father, John Farland Sr., at Boston University when she finished with us. So this is an arm. So these were arms rather than this, but they've split the arm into the bicep into what they're calling proximal, which is the top half. Okay, the middle, and then the distal half, which is down kind of closest to the elbow. And they were doing fast training, slow training, and then a control. The dark is the gray is their eccentric arm. They did eccentric only. The white is the concentric arm. And so what you can see here at the proximal side and all of these things, when you go fast, you get a bigger change in cross section when you do eccentrics, right? Fast training, eccentrically, you get a lot of force. You get just as much force. When you go slow, they're really kind of about the same, okay? Because the force is much closer to the eccentric. This may not be anything magic about the eccentric contraction itself, other than the fact that you can go fast and lift with a sufficient amount of force. And this is some interesting data. We played around with some stuff like this and never bothered to publish it, but just showing sort of hypertrophy was reasonably similar across the length of the muscle. Okay, so whenever the bros next door tell you, like I'm gonna do decline bench press, or I'm gonna do the hammer curls versus the regular curls because that works the bottom part of the muscle more than the top part of the muscle. No, wrong, false. Okay, doesn't do that. Okay, kind of hard to target one part when the whole thing is contracting. Motor units, your muscle fibers are relatively evenly distributed across all of them. You're going to get some stuff there. Everybody has different anatomy, so they may appear as though, oh, you have a lot of muscle, you don't have much distal muscle, but much more mid and proximal. Everybody's anatomy is a little bit different. But the data tells us that we, for the most part, tend to see sort of the stuff being spread relatively even. Okay, and this is just changing torque. This is back to the adaptations are specific. When you train eccentrically, shockingly, you get better doing eccentric contractions. When you train kind of concentrically, you're going to get a little better at concentrically. Okay, so some other kind of interesting data that's out there on all of that.
The load wasn't the same, though, right?
No, the load is not the same. Load is not the same. That's correct. That's correct. It can't be. Right? You can't do fast and have the same load, right? So it's got to be different. Now we need to go back and look, and we can pull up the article and figure out. It's also possible that they did the training on a dynamometer, and so it's like go as hard as you can and do like 10 eccentrics as hard as you can and 10 concentrics. Now we need to check.
You would expect it.
Yeah, I would expect the torque to be lower in the concentric for sure. And so is it a consequence of the contraction, or is it just a consequence that you're getting more force, right? If you get more force, then you might expect there's more work being done. There'd be more.
About the speed.
Speed, my guess is the speed exerts its effect by altering the force production, rather than the fact that the speed, there's something about the velocity itself that matters. I think it's the effect the velocity has on the force, but I could be wrong. I'm aware of data that if you lift a heavier weight, that seems to be better. There's not a lot of stuff on speed because you can't match resistance at different speeds, right? Unless you're going to do very, very low, like the matching of very low weight. It's constantly when you go faster. Okay, so, and again, if we had more time, and Dr. Ferrer may talk more about some of this stuff, I can have Dr. Mike come in and he can do a whole class just on this. So what I'm going to show you guys now, we talked a little bit about the kind of contraction. The kind of last piece of all of this is the idea of a metabolic trigger. Okay, is there something about the load? Is there something about going to task failure and accumulating getting to a certain kind of lower acidic pH level, accumulating metabolites, driving a certain amount of water in or something? Okay, is there something to all? And so what I'm going to show you guys, and I should probably flop these two things around. What we're going to do, this is a very, very famous paper. This is this Tucker paper from 2000. And then there's been a lot of stuff since all. These are data on something called blood flow restricted training, or KATSU as it was originally termed. Okay, and the idea behind all of this is I put a blood pressure cuff here on your arm, and I inflate it enough that I can maybe partially occlude arterial flow in, but I can sure I can occlude venous return from coming out of the heart. Okay? And the consequence of that is that you fatigue faster at any given amount of weight that you're lifting because you may be somewhat restricting arterial inflow. Okay? So what you can see here, and I apologize, there's a bunch that is on here. This is very common with a lot of these things. Okay? You have conditions where in the black circles, okay, this is back. The y-axis is showing creatine phosphate levels in the muscles. This is done in an MRI machine. This is done in the night. And what you can see then is what is happening as we change. What's the change in PCR levels? Now, I'll explain why this is important in just a second. Okay? So here is what we're going to call, this is low load exercise. This is doing weights with 20% of 1 rep max. Okay? So if you can do knee extension with 100 pounds, we're going to give 20 pounds and have you do reps for 20 seconds. So you will note that there's a little bit of a depletion of creatine phosphate and for the most part it's off. Okay? Not going down that. These open circles here, okay, this is high low. So what this H stands for, that's at 80% of 1 rep max. That's a very kind of traditional, we're going to do a set of 10 reps or something with 80% of 1 rep max. So you will note from those, okay, this is with full flow, normal blood flow into and out of the muscles, much more creatine phosphate depletion at the high load than at the low. Does that make sense to you guys? Yes, no, maybe. Skillet, you with me? You okay? Does that make sense? Why would the high load deplete creatine phosphate more? What would that tell us? It is as obvious probably as it seems. Right? It's okay. We use creatine phosphate when? Okay. So if I'm depleting a lot of creatine phosphate, what might that tell us about sort of the relative intensity of that exercise? Do you think if it goes down, you know, this is going down 50% or 60%, that I'm going to be able to continue doing that for very long? Right. You're 100% right. So the creatine phosphate depletion is giving us an estimate of sort of the anaerobic metabolic cost of what's happening. So very hard, lots of anaerobic things going on here. Fatigue very soon at the high load, not so much at the low. These other ones, the triangles and the different squares, are going to be sort of moderate pressure or high pressures in the blood pressure cuff, lifting 20, 30, or 40% of 1 rep. And all I want you guys to appreciate is if we look at these, I can lift the same 20%, and if I partially include blood flow going to the muscle, I'm going to get a creatine phosphate depletion that looks a whole lot more like high load training. That's the idea. Okay? Metabolically restricting arterial flow in is going to lead to fatigue faster at these low levels. So I'm not having to lift as much weight, but I'm going to reach fatigue at about the same time. So this is important because if you look at this study that was done well before this very famous Paparata study, what you're going to see is the 3 bars. There's 3 sets of these bars. We've got the biceps brachii, the brachialis, and then the triceps, okay? And we've got low load with occlusion, okay? 20%, no, sorry, 30 to 50% of 1 RM with occlusion, 30 to 50% without occlusion, and then high load, which is 50 to 80% of 1 RM max. So this is training with this, and what you note then is this is, I believe, MRI assessed changes in the cross-sectional area of the biceps when you're doing this. Or maybe, yeah, the biceps. Okay. Low load with occlusion is at least as good and maybe better than high load, way better than low load without occlusion. Okay. Now, I can remember seeing this paper a couple of years after it came out when I was a grad student and thinking, there's no way this is made up. This isn't a thing. You can't lift 20% of your max and manage to make your muscles get bigger. Okay? Now, there's potentially some issues with this exact paper and that magnitude of things, and the time course of it was pretty significant. Okay, but it's been repeated 1,000 times since then. Okay, 1,000 times. And one of my best friends did a similar version of something like this as part of his dissertation and found roughly the same. So what we think is happening is, if we would normally think that load is the important thing, here, doesn't matter what the load is, it seems like maybe reaching this metabolic endpoint, this point where we've depleted a lot of creatine phosphate, we've probably built up a lot of lactate, we've fatigued ourselves. Maybe that's the important thing for us to be able to do. Okay? And so the argument, although it's not actually ever been done very much, it needs to be done, but there are some safety issues, is, okay, let's take your grandma who can't regularly do squats and put a blood pressure pump on her, a fluid flow, and let her do squats with her body weight and see what happens. Maybe we can take people that would have difficulty performing, and it would be unsafe to do this high weight, high load exercise. And we can do this in older adults, people that are post-stroke or that are post-rehab or something like that, and do this lighter weight with a little bit of occlusion and see if it matters. NASA has played with this, just with a lot of different things, trying to figure out what the metabolic trigger is or isn't. We still don't fully understand all of this, but there's some really kind of intriguing stuff. Okay. And I meant to look it up this morning and put it in here. I don't think I have the thing, but there are some other papers where they don't even do the occlusion. It's just low load, 20% of 1 rep max, lift until you get to failure. So that means you do 30 reps, you do 30 reps. Okay. Moderate and high load, you do all of those. And as long as you do sort of every set to failure, then over the course of 8 weeks or 10 weeks or something, we see roughly similar increases in muscle size. So maybe really. So there's some interesting things. I'm going to mention periodization, and then I'm going to tell you guys that I don't care if you know what you're doing when you train, then you're going to do it anyway. And people wring their hands, the bros wring their hands over it. It makes me just want to yell and scream a lot. So the idea of periodization is change. Okay? Is change. So I got this is from an undergraduate exercise phys textbook. This is from a paper. I don't remember where I found this. But so the idea with periodization is, okay, this week you're going to do 3 sets of 8 reps with 85% of your 1 rep max for 3 days. Next week we're going to do 3 sets of 10 reps with 80%. So you're doing something that's a little bit different. Okay, a little bit different. Then we're going to increase either our volume or our reps. We're going to go up 1 week and down the next week. We're going to just kind of change it around. And maybe it's not even week to week. We're going to do 3 sets of 8 for a month. And we're going to do a month of 3 sets of 6 or something. Okay. So this is what is called linear periodization. Whatever it is we're doing, our sort of, this is week by week by week. And what you can see is we're doing percentage of 1 rep max. It's going to be here. Right, this is the number of reps that we're doing, but we're sort of basically going up and then we come back down. We go up and we come back down. This is like a 4 or 3 week kind of linear upwards periodization. This is called reverse linear periodization, where you do a higher volume and then you kind of slack it off over a few weeks, right? Then you go back up and you slack it off. That's called this. Some people will say you should do either the linear or the reverse linear within your days per week. So Monday, do sets of 15. Wednesday, do sets of 8. Friday, do sets of 4. And I've gone cross-eyed and I really don't care. Okay. There have been an inordinate amount of studies done on which one of these things is better or worse or slightly better or slightly worse or whatever, okay? This is weekly reverse linear periodization. This is sort of basically monthly reverse linear or monthly linear. There's a thing called undulating, which would be high on Monday, low here, back up high again, where it just changes from day to day. There's undulating, there's reverse undulating, and I seriously, really still doesn't matter how it goes. Okay. The take home from all of this, okay, is if you do your programming correctly, you're going to get this by simply getting progression and making it over. If you lift something and it becomes easier and then you make it hard again by changing something, you've basically done some level of periodization. Okay. Now, when you're just doing weights, it's one thing, it doesn't matter that much. Where it becomes much more probably important is if you've got actual team sports where people are doing resistance training and aerobic training and skill specific training, and they have an off season and an in season, and they're trying to match up, right? I need to be able to perform right now, but I also need to be able to maintain whatever strength I've accumulated while also still being able to practice. And so there's a lot more to having to match all of those things together, okay, than just I'm a bro and I want to see what's happening with trying to make my muscles bigger. Right. So in that instance, the actual programming of in and off season and out of season stuff to match all of those things up is important. But just our next door bro is maybe less so. All right, maybe less so. You'll get the sense I'm not a big fan of this. People tell you they're just trying to sell you something. They want to train you, they want to sell you on their program, they want to do something, right? They got an infomercial on their TikTok. Okay, talk about this. Okay, so we're going to finish off the last couple of things on all of this by talking about what do we think are the hypertrophic signals? What do we think are these cellular signals that are going to drive protein synthesis, and what do we know about those kinds of things? Okay, we must be in a net period of anabolism for some minimal period of time, a month, 6 weeks, something like that, okay, in order to see measurable, noticeable increases in muscle size. There are many signals that are integrated very likely that control myofibrillar protein synthesis, that control making of actin and myosin and muscle changes. We get into trouble, like I just showed you guys with the eccentric versus concentric exercise stuff, when we look at the acute response, okay, and what happens following one bout of training. The assumption is Jordan goes, she does squats today, we take a biopsy, we measure for hormones, we measure for messenger RNA for things in her muscles that are going up, and we want to draw the conclusion that if it changed today, after that one bout, it likely is going to contribute over time to her muscles getting bigger. And that may be the case, but it's not always the case. Some of these things are, and the idea is that, oh, well, if we can maximize this thing in your one bout and you keep doing that, then that ought to give you the biggest chance to get the biggest muscle. And the research does not always bear all of those things out. Okay? One bout of training tends to lead to a net positive protein bout, where synthesis seems to predominate over degradation, or at the very least, where you get less degradation than you would if you had done a different bout. Okay? So the idea then is that something, hormones, some signals, something is driving all of this. And the hope then is that if we can drive that multiple times, right, over the course of, a month or 6 weeks or 8 weeks or 12 weeks, that eventually we'll get bigger muscles. Okay? Eventually we'll get bigger muscles. Okay. So more data from Bob Wolf's lab and the guys at Galveston. what we tend to see, if you look at an acute change in protein synthesis rate, so this is the fractional rate at 6 hours, 1 day, 2 days, 3 days after a bout of exercise, after a bout of resistance training. Okay? We tend to see elevations that are maybe statistically up out to 3 days afterwards. They tend to peak at about 24 hours afterwards. Okay? So what we see with all of this is that after you do things, synthesis goes up, degradation also tends to go up. Okay? And then feeding with protein may blunt some of the degradation and then get you a little bit bigger. This is a net. So this is the balance of synthesis minus degradation that's kind of going on. Some degradation is probably good. It's probably activating satellite cells and some of those kinds of things. You don't completely want to blunt degradation necessarily. Okay. Here are some older data looking at all of this. That this is synthesis before and after training, breakdown before and after training. And then here's your net balance, and you're going to say, Dr. Black, how can I have a negative net balance and actually get hypertrophy? And I'm going to say, I don't know. Again, this is measuring, this is what we see like a day afterwards. Okay. Well, we have to be cautious with this versus other things. Now,
Has there been any studies where they tried to blunt degradation?
So I'm sure the answer to that is yes. And one of the ways that we can do that is by feeding protein. The other ways that we can blunt the degradation, and I would need to look. So you could also, you could give, say, ibuprofen. There's some other, I forgot what the supplement is, but it's a supplement that inhibits the calpain enzyme, so it inhibits the stuff that drives a lot of the apoptosis and the breakdown. And I know that if we do that, we see a little bit less accumulation of immune cells, we see a little bit less muscle damage afterwards. And my assumption is if we were to look at degradation in that period, that it would be a little bit blunted. But I'm not 100% certain of that. But I'm sure somebody has done that. It's a great question. I don't know the answer to that. You can do it. It seems plausible, but that would also give us some insight into how important the degradation actually is, right? But if we want the degradation, you're in a larger balance, then maybe it works. I don't know. Okay, so this is just showing fractional rates. Okay, this is 3 hours post fractional rates. These are all from the same thing. They're trying to show synthesis and breakdown, and then this balance, which is just the difference of these two kinds of things. But if you look at the actual fractional rate, which is slightly different than what these things are, this is a little bit more. This is a volume difference, and it seems like it goes up. Okay. So we know that resistance training drives this increase, right? Drives this increase. And so then what the question that has driven a lot of us on all of this is, well, what's that doing? What is it about the training? What is signals are getting turned on or off that are leading to a lot of this? So there's been a fair amount of interest in anabolic hormones, okay? Testosterone, growth hormone, and then one that some of you guys may have heard of or learned some more about, something called insulin-like growth factor 1. And insulin-like growth factor 1 comes in a couple of isoforms, a couple of flavors. One that gets released by both the liver and muscle, and then one that only comes from muscle, which is called mechano growth factor. It's the IGF-1E variant. And so we know that if we give people testosterone, your protein synthesis rates go up. We know some of that by, if we have men that don't make enough testosterone, you take hypogonadal men, you give them testosterone to get them back to what we would assume would be a physiological range. They get about a 15% increase in muscle mass and about a 50% increase in protein synthesis. If we give it to eugonadal men, so we give testosterone to guys that have a sufficient amount. They do no training. You just get testosterone. You might get 20% bigger muscles. Okay? Sit on the couch, eat flaming hot Cheetos, get bigger muscles. Okay? Seems pretty great. Okay? Now, that may come with testicular cancer and back acne and roid rage and a whole host of other things. But it illustrates the point that for sure, if you don't make enough, you don't have enough testosterone, that can be a problem. And if we give you more than you would normally have, that makes your muscles bigger as well. Okay. Similarly with growth hormone, if we give it to you extra on top of things, you get more mass, more strength, more protein synthesis, decreases in breakdown. But when you give growth hormone and then you train, we didn't talk about it. If you give testosterone and you train, we're not really sure how big it is. Just giant potential. Okay. Growth hormone doesn't seem to work that way. Again, very, very few studies. But if we supplement you with growth hormone, you're going to get bigger muscles just by taking it. If we supplement you and you resistance train, you're not going to get this sort of additive effect, okay, that you see with testosterone. Growth hormone, again, though, you get testosterone. Testosterone, anybody knows anything about endocrinology, testosterone signals for the increase in growth hormone. The increase in growth hormone signals for the release of IGF-1. So there's this interaction between all of these things. And is the exercise component driven by testosterone? So supplementing here doesn't do this, or the supplementing here decrease your testosterone. There's some feedback mechanisms that are involved in the midst of all of this as well. Not a lot on supplementing IGF-1 or MGF, but what we do seem to know is that MGF, this mechanogrowth factor, is only released by muscles, and it seems to be maximally released when you are stretching a muscle under tension. How do I stretch a muscle? What kind of contraction do I need to do to stretch a muscle? Okay, eccentric. Okay, so there's something, when I say there's something magic about eccentric contractions. It may be some of this. Muscle contractions also tend to upregulate the receptors for these hormones, especially IGF-1. Okay? Especially IGF-1. So when you do contractions in those muscles, that's why when you lift with your arms, your legs don't get bigger, potentially. You create the environment in the arms partially by they've contracted, we increase production of receptors for these hormones at that place, especially IGF-1. That muscle that's contracting releases mechanogrowth factor that then turns around and binds back onto those receptors on that muscle that have gone up, and potentially this one activates satellite cells. MGF activates satellite cells. Really, really important. Okay. So I will show you guys, if we kill your satellite cells, you don't get hypertrophy. Don't get hypertrophy. You don't want to kill your satellite cells. I have to give you, but would likely also be a lethal dose of radiation to do this. You can do it in animal models. So all of these things go up after a bout of exercise. Okay, Chris, I'm going to come back to you in a minute. All of these things go up after a bout of exercise. To what extent does that acute change matter? We don't fully know or appreciate because of the complex interactions between all of them. But you can see here, right? Testosterone goes up. Well, there's a 50% increase in synthesis, but only a 15% increase in mass. And so it's just a little bit different across all of these things. Okay? And it goes up one time. You know what goes up when you run? Testosterone, growth hormone go up when you run too, because they mobilize fat out of adipose tissue. They cause the breakdown of liver glycogen. Right? They function like glucagon. They're providing substrate for all of these things. And yet, you run a bunch, you don't get giant muscles. So, okay. Chris first, then Matt.
Skip my question.
Sure?
Yeah.
Okay, Matt.
When increasing satellite cells
With increasing satellite cells, increase hypertrophy. I don't know.
can use.
Can we increase satellite cells? It's an excellent question. I'm honestly not certain. I don't know how we would go about doing that. Inject people with satellite cells. It's a, what would be interesting for me to know, maybe somebody has looked at this. So if we know that there are these genetic components that control hypertrophy, right? People that have normally or genetically are higher in testosterone probably tend to have more muscle mass than people that are low. It's especially prominent if you look at women. Women that have higher testosterone levels generally have somewhat blunted secondary female sex characteristics, okay, and tend to have a little bit more muscle mass. That's a part of that. A little broader at the shoulders, a little bit narrower in the hips. They look a little bit more kind of that in that less secondary sex characteristics. Maybe one of the other ones is where some people probably have more satellite cells. So why is that? Does that matter? Is that important? How do we go about actually testing that? How much of a difference is irrelevant? That's a tricky, right? Because if you don't have any satellite cells, if you have very low numbers and you're going to trash your muscles and never going to repair, you're probably not going to survive. And so it's kind of a tricky thing. I think there's a little bit of evidence that maybe as we age, we may lose some satellite cells. And that we know that when you get to be like over 80, you can't make your muscles bigger anymore. You can hang on to what you have, but you can't make them bigger. Is that because you've kind of reached the end of the line with satellite cells? I don't know. So, Matt's going to engineer for us some satellite cells and some mitochondria to inject into our muscles in a particular way. Right? So, I don't know. It's a good question. Chris, your shirt, no question. Wants to come back? Okay, Gabe.
I know you argued that the circulating hormones are not very important.
I didn't argue. No, be very careful. I just said that the role that they play is somewhat under question. I will say that. There is evidence from Stu Phillips that they don't matter at all. That the acute change in any of these hormones does not correlate to longer term increases in muscle mass and those kinds of things. That whoever has the biggest testosterone response after one bout of exercise is not necessarily the person who's going to get the biggest muscles. And whoever has the biggest increase in growth hormone is not the person who's going to see the biggest increase in their muscles. But I wonder if some of this is that it is necessary. You have to have a response in order to get the hypertrophy. But this isn't the only thing. It's a piece of the puzzle, right? As long as you're getting this or a sufficient amount of this, then something else is the thing that plays the factor. But we know if you don't have some of these, you're going to have small muscles. It's not going to work. And we know that if we give you a bunch of this, then it is going to work. So I think it's just a kind of a semantical way of trying to kind of parse that particular argument.
Like you on the same side, you deliver
Yeah, this one's important. We know this one is important. The other one's probably to some extent. We didn't even talk about insulin, right? And there's some other things that go around with these IGF-1 and insulin. If you take carbohydrate with your protein, insulin is also anabolic and it drives those things in. And you need the sugar to help drive the glycogen resynthesis and also to activate. And the muscle then knows that it has a sufficient fuel reserve to kind of drive and handle having more fiber. So there's more. It's a really complicated sort of thing. It's really complicated. Then we can spend an entire class just talking about these kinds of things. So, are the anabolic hormones important? I mean, you need to have the release. So what is the stimulus? We know that loading matters, we know that stretch matters, we know that total muscle mass used matters. Okay? Something about inducing mechanical stress along the outer membrane of a muscle fiber seems to activate mechanoreceptors. They're going to aid in the release, especially of IGF-1, the BGF inside there. We're going to get additional hormones as part of the systemic response, and then with that stress on the membrane seems to lead to the upregulation of the receptors. Okay. I think I told you guys last week, we do an unloading model or an inactivity model where we put you in a cast. Whatever muscle is stretched when you're casted doesn't shrink, whereas the other one, gone. Okay. And so there's just something about being. Okay, so a lot to me, and I'm gonna again maybe say something that's mildly controversial when we're going to be done with class. Okay. To me, all of this fuss about the role of hormones, in some ways, can be traced back to this paper, okay, from Bill Kramer, who is a big friggin' deal. He's the department chair at Ohio State now. Big deal. One of the founders of the National Strength and Conditioning Association. If you read one of their older books on their idea to train, it's all based upon this. Okay? It's all based on this. They measured, this is the growth hormone response to a host of different kind of training protocols. And I just want to draw your attention to this one that we see right here. Okay? And what they found was that when you train with a short rest period, do a set of 10, wait 45 seconds, do another one. Don't wait 3 minutes or 5 minutes for all of your creatine phosphate to come back. Short rest periods, that's what this is. Much greater, okay? Much greater serum growth hormone levels. Now, those of you in endo, we can argue should this have been on a log scale, or we're talking about some other things here. It was 1990. Okay? So we see this big increase in growth hormone. So if you guys ever hear or see things where people talk about hypertrophy training, what they're going to suggest is I'm going to do moderate weights, so like 8 to 12 reps with a short rest period, which we argue then gets us a bigger growth, acute growth hormone release. That's why we do quote unquote hypertrophy training, because we're going to get this and we think that's going to drive a larger increase in muscle mass. I am not aware of any studies that demonstrate that doing this actually results in more muscle mass. Okay? But it certainly will potentially, and I'm also not aware that anybody's ever replicated these findings on things that we get this bigger increase in growth. Okay? But I mean, literally the entire NSCA, like their CSCS training book, talks about this. So, just going to leave you guys with that. Okay. All right. We're good here. We will pick this up on Wednesday and we'll finish off resistance training. And then that will leave us next week to talk about other things. None of you asked, which I appreciate. You will have your test on